Okay. So, good afternoon, everybody. My name is John Hebenid. I go by a bunch of different names. PhD, Björkus Dorkus. I do a lot of yelling on Twitter. I'm still currently a student, unfortunately. Working through that with the pandemic, kind of threw everything off a little bit. But this is my first time, I guess, coming back and being able to speak in person rather than just online, which is pretty fantastic. And so what I'm going to kind of talk to you about today is going to be not necessarily a topic that's going to be immediately practical to your software engineering endeavors, but sort of talking about the direction of a programming language that a lot of us in this room use daily, or at least did use daily, or have to interrupt with daily, or struggle with daily, and it's C, right? And I want to talk about the idea of C coming back, right? So it wasn't necessarily dead because it was kind of everywhere, but people had sort of consigned to the idea that, like, oh, it's not going to see updates anytime soon. And if there are updates, they're not going to be very significant, and no one's going to really do anything with it, and so on and so forth. And that could not have been further from the truth. There was an explosive number of additions in the latest release that is going to be C23, which is in tradition of C89, C90, C99 being published a year later, C17 not being published in 2018, C23 is going to be published in 2024. It's just scheduling, and you have to get ISO to agree to stuff, and you have to do balloting and do national body comments. The ISO process is very heavy. Yes, the standard has an off by one error, which that's why it plagues you, because we didn't get it right when we keep publishing the standard, right? But the one time we do get it right, all the off by one errors will disappear. I hope. I'm hoping that's like a cursing, because if it's not, then we're all just we're in trouble. But yeah. So specifically, I want to talk about C coming back into the zeitgeist, I guess, and more importantly, I want to talk about this idea of unbreaking this charter, right? And so what do I mean by charter, right? So generally, a charter for any organization is like your goals, your mission. What am I going to do? What are we going to do out in the world? What are we, how are we going to help people, or maybe not help people if that's what your mission is? I hope that's not your mission, but you can say whatever you want in your charter, and that's supposed to define your organization, your goals, your mission, right? And so as a standards body, you don't actually have to have a charter, but we do have one for C. In particular, we have one for every major revision of C. We usually put out a charter that defines what it is we're doing, right? You can see the 1994 one is a little bit too old, so we don't actually have like a link to that one, but we got one next year, right, from talking about C9X charter, right? So this is one is talking about C99, right? So we're past the C89 threshold. We're coming up on like 10 years old, or getting closer to the 10-year-old threshold mark, which is about every time we release a standard, right? Once every 10 years, basically. And so we have a C9X charter, we have a C1X charter for C11, and then we have a preliminary C2X charter, and then we eventually got to an actual C23 charter, with like scheduling and other stuff, right? And the authors of all these papers are conveners, the people who were leading the committee. So I think at some point, Robert, you might actually have to be responsible for writing the charter and telling us what we're going to be doing with our lives for the next, I don't know. I think you said you were committed for 3 years at least.
Minimally 3, yeah. My plan's actually probably
6 years. Okay, so 6 years. You heard it here first. 6 years. But the idea behind this document is that it tells us what exactly the committee wants to do and what exactly the standard is supposed to be for, right? Who's it supposed to serve, who we're supposed to be helping, who we're supposed to, I wouldn't say hurting, but maybe who we're not supposed to be prioritizing, right? Things we're supposed to be focusing on, that sort of thing, right? And so kind of as we did this, there's some particularly notable principles or things that kind of pop out from this document, right? Now, all of these have like C89 and C99 and C11 and whatever listed on them, but what's important to note is that all of these principles actually still remain the same more or less throughout the entire duration of the standard, right? Each time there was a charter, all we really did was add additional principles. We didn't really remove any or change too many, except for like in one specific case where I'm going to talk about that a little bit. But in C89, it was about existing code, right? Like there was a bunch of code written on K&R from the 70s and 80s, and they had to make sure that that stuff kept working. And so a lot of that focus was on existing code, make sure the code worked. But they kind of said, yeah, we can throw your implementation in the garbage, right? If you write an implementation and we make some changes and your compiler falls over, well, that's your problem, right? In practice, that's not actually what happened. We actually bend over backwards to accommodate compilers and implementers and being able to implement things in the worst way possible. We love the term called quality of implementation, where we say you can have a really good implementation, and then we kind of leave off the fact that you can also have a really bad one. But what we said is that existing code is very important, and the idea is that the standard is this kind of treaty between you and your vendor, right? Your implementer, the person who's giving you your compiler and maybe your standard library and any other utilities that come along with it. C99, we were trying to focus on simplicity, which not sure we hit that mark, but we definitely tried. But that was the focus for C99. It was like maintain conceptual simplicity, kind of focus on that. C11 was more about trusting the programmer, but then we kind of realized around C11 times, like, oh, we've got a lot of, like hacking became real, like in like the 21st century, like it started actually hitting a lot of people, a lot of targets. It started blowing up a little bit. And so for C11, it was like, yeah, we should trust the programmer, like, as like a thing that's like a general purpose thing. But, when it comes to security, we should probably maybe tone it down a little bit, wind it back some, and go about that way, right? And then finally in C23, we added just one principle, and that was that APIs that we write should be kind of self-documenting, right? So if you can use an attribute or something else to describe what is going on in the function, whether or not it modifies global state, or if what the size of the array is where possible, you should use that kind of markup, right? That is available in the standard that almost nobody knows about, right? Question, who here knows about static array extents that you can use on parameters? One of you, and you're on the committee, so yeah, it's C exclusive. It's not supported by C++, which is why it's usually thrown out, because you have a header file, you try to use static extents to document your API, and then you have to throw it out when you compile with C++, or you get a bug report because someone's like, I compiled this with my GCC, G++, whatever, and it broke, and it's like, what is this? And it's like, oh, it doesn't matter, and you just throw it out, and then you go back to just using raw pointers. Okay, but we tried to say that where possible, APIs should be self-documenting. Right? They should describe themselves, right? So if you have a size, you can, add the array extent to the parameter and put static in there, and then put the actual like parameter name, and that would like describe like this is an array of at least size n and stuff like that, right? And so we wanted to make sure that this was self-documenting where possible. Yeah, it's also not. Well, I mean, Microsoft's is a C89 compiler with extensions, and that's kind of how to treat it, unfortunately. But they are making leaps and strides in improving their support for stuff. So they might not get static extents. They probably figure it's just like not worth supporting. And I mean, they wouldn't be too terribly wrong because most people don't use it. But they are making improvements. But we'll talk about Microsoft and the things they did in particular, and their effect on the ecosystem. Specifically, one of the things that's in this giant charter document is this idea of keep the spirit of C, right? So, you have all these things, right? A, trust the programmer. B, don't prevent the programmer from doing what needs to be done. C, keep the language small and simple, which constantly gets thrown at me. Provide only one way to do an operation. Robert mentioned this in his keynote earlier today. E is you have to make it fast, even if it's guaranteed to not be portable, right? And F is something we added and we kind of shoveled in there, at C11 time when, the world was on fire and we were getting a lot of CVEs and stuff. We said make support for safety and security demonstrable, right? And that was kind of temper A, right? We had to trust the programmer, but not all the time, right? It's a trade-off, that sort of thing. Did we do that, right? Did we actually achieve that goal in standardizing any of the versions of C that we've been standardizing so far, right? So all the way from C99 to C23, have we been doing that? Have we been following our charter, right? And And it really depends on who you ask, right? Some people think that C23 is going to, set the world on fire and destroy everything. Other people think, we've wrecked the process and we're doing everything backwards and inappropriate, and that's why we keep making worse and worse standards. That's it from their perspective. And other people think it's like it has some really good improvements in there that they want, right? It really does depend on who you talk to, right? But we're going to kind of go through some very specific pieces of criticism from both inside and outside the committee. So this was a paper from someone inside the committee, Martin Seabour, very long time C member. I think he dates all the way back to. I like how I'm dating committee members. He dates all the way back to mid-late 90s, been on the committee for a while, been helping people, been implementing stuff at GCC and in other places for a long time. And so he kind of wrote this paper during like the end, like 2020, 2022, about how we've been standardizing stuff for C23 in particular, right? And basically, his contention was that we were kind of violating the charter, right? A lot of what the charter said is that we're not supposed to be, that we're supposed to be codifying existing practice, that we're supposed to be taking things from things that exist in implementations, right? That we're not supposed to be inventing things, right? And especially in C11 and later on, we really doubled down on that when we put a clause, no invention, no exceptions, right? Like no exceptions to not like no exceptions like C++ exceptions, but like no exceptions to the rule of not inventing anything. You're not supposed to invent anything when you put it in the standard, right? You have to cleave as closely as possible to existing practice. And we kind of did and kind of didn't, right? There's some new things that come in there that didn't show up in any other languages, and there's some things that had lots of existing practice that existed in a lot of different other places. But this was kind of Martin's kind of saying, like, we need to pump the brakes and kind of look at what we're standardizing and what we're doing in the standard, right? Of course, it wasn't just inside the committee, it was outside the committee, right? This is a paper called How ISO-C Became Unusable for Operating System Development, which is just a fantastic paper title. But the contention that Victor has is that because of the things that people are doing with undefined behavior in particular, and the way that compilers are optimizing code these days under the rules of ISO-C, that makes it less suitable for doing actual operating systems work or other systems programming low-level work tasks. And so that was Victor's contention when he wrote this paper. He shipped it out in January. I guess I wouldn't say he's outside the committee because like he did show up for like a time. He was like there, and then he was there for a while. He kind of observed, watched, participated, got on a lot of people's nerves publicly. This is not like private stuff. He did that publicly, unfortunately. And then he kind of left and then published his paper. And so kind of the contention of his paper was that, if you're going to be writing for operating system or whatever, you're not really writing ISO-C, you're writing, some special flavor of C, right? That is, chock full of compiler flags. Like, so, you want to have flags that, with well-defined wrap on overflow, right? You want to have flags that don't, that prevent the compiler from doing things like deleting null pointer checks if you use a standard library function, because all standard library functions do not accept null pointers as an input, and it's undefined behavior to give standard library functions from C null pointers. So if you give it a pointer and then you try to check after that function that null pointer, the compiler will just delete that check because like it's not supposed to happen, right? You're never supposed to give a null pointer to stir copy to whatever, right? Or mem copy or similar to that. And that actually did eventually result in some vulnerabilities in certain places. Because again, a lot of people like to pair null pointer with the size of 0 rather than like some funky pointer that like is of size 0 with size 0. And so naturally, when people are just writing normal code that happen to have null pointer plus 0, you delete some checks and suddenly you're scribbling over the bootloader of your very important modem or device or a small thing that's supposed to make sure you don't crash. And that's not good. So that's the perspective of this paper, right? It talked about undefined behavior. It talked about from the perspective outside, rather than like, are we standardizing things correctly? This was the things you are standardizing do not help us as systems programmers, right? And so this was a different perspective. Then there was yet a third perspective, unfortunately also negative, that C23 was basically I wouldn't say dumpster fire. He didn't quite call it dumpster fire because he does praise certain things, but he says that, standardization is the whiskey tango foxtrot, which is, just a fancy way of saying WTF, which is, what the, exactly. And so again, Terrence Kelly and Mr. Pond wrote this paper, Catch 23, the new C standard sets the world on fire, right? And in this one, they lambasted a lot of different things that did and didn't go into the standard, right? Like, so real lock becoming undefined behavior was a particularly fun target that came out of this paper, and a bunch of other stuff that we changed in C23 that I'm also going to have to talk about as we go forward. So that's a lot. That's a lot of negativity. I, of course, write a lot of positive stuff, so I'll kind of be focusing on the negatives. So this talk might be a little bit depressing about C23, but we're going to kind of talk through a lot of that negativity and like what's what and how we can kind of approach it, really. So the first thing we have to ask is, are we failing, right? Basic question to ask. Are we failing in our mission, right? We have a charter, we have a set of principles, right? We're supposed to codify existing practice, we're supposed to trust the programmer, except when it comes to security stuff. We're supposed to make sure that we, give them the tools they need to get the job done. The code can be both portable and non-portable, right? Where did things go wrong, right? Where are we going wrong? What are we doing wrong, right? Or is it maybe the charter that's failing us, right? Do we not have the right set of principles? Are we guiding ourselves in the wrong direction? And that's why we keep making, what people consider to be mistakes, right? And we have to ask ourselves, like, is the spirit of C like dying, right? Is this idea of a simple, small language that, can be compiled by everybody, but has like this universal appeal and that works everywhere, right? Is that spirit going away? Are we losing it, right? With C23, are we losing what made C good, right? And are we going to keep losing it as we keep kind of chasing features and fixes and whatever else, right? So that's kind of the bigger question around all of this, right? Are we actually doing something proper in service of C? And this is the spirit of C gets thrown at me all the time, right? It doesn't matter what discussion I'm in. New feature, old feature, bug fix, talking about undefined behavior, right? I always hear about the spirit of C. Like, it's like the ghost of Christmas past come to tell me about, how evil and Scroogey I am. But, obviously we have these, these principles, right? You're supposed to, don't prevent the program from doing what needs to be done, keep the language small and simple, right? This is supposed to be the spirit of C. This is literally, there's a heading called the spirit of C, and then this comes after it, right? So A through F, this is what's in the spirit of C, right? This is what the charter says the spirit of C is, right? And of course, people, take one of these lines and slap me over the head with it whenever I write a proposal or something, and that's usually what, they say the spirit of C is supposed to be about. So obviously, right, there are the full set of principles. I showed you a glimpse of them before, but really, C89, we had existing code is important. C code can be portable. C code can be non-portable. Those two sound contradictory, but the idea is that, there's some stuff that can be portable, and then there's other stuff where you just have to let the vendor make an extension, and you can't really, I can't really properly describe your bus memory with your, chip memory and all that stuff correctly. I'm just going to assume that's all unified address space, but like, you can write some things that might be non-portable that will talk to the fact that you'll know the fact that you are dealing with several different address spaces, right? So obviously the ports that are portable are the stuff that we define. The stuff that's non-portable is undefined behavior and, implementation defined behavior and unspecified behavior. 3 different kinds of traps for you to run into. And then your vendor extensions that go all around that. Obviously, we want to avoid quiet changes. So when we break something, we want to make sure that it's a compile time break. So we don't change something and then your code just silently does something different and then everything explodes, right? That's, that's bad. Obviously, we have the treaty between the implementer and the programmer, right? Every time you compile the programmer, you basically shake the hand of your implementer and they say good luck and you say thank you. And then you hope that, you get a good programmer on the other side. That's part of it. Obviously, it says keep the spirit of C, which references that list. And then C99, we had support international programming. That was when everybody was like on the POSIX and locale kick. And so we put that in there and we put a bunch of locale and global mutable state. And everybody was happy until we started sharing stuff. And then everybody was sad because, you called the library function and it changed the locale of something or messed with the locale. And so this library all the way over here that didn't have anything to do with you is broken now because you changed to using the comma for your decimal point, and that was expecting a period, and now everything's gone to hell. And so a little bit iffy, but we do have support for international programming. Codify existing practice to address evident deficiencies, right? So always focusing on existing practice. More principles, right? So we're about 15. So in C99, we continued with that. We got minimizing compatibility with C89, minimizing compatibility with C++, maintaining conceptual simplicity. And then in C11, we added some more, right? We had trust the programmer, but that's kind of outdated, because security, and we're getting our butts kicked in, in all of these CVE databases. We wanted to say that there should be no invention without exception. That's very important, right? We're not supposed to do anything unless a compiler vendor does it first, right? So they got to do it first, and then we follow what they do. And no inventing stuff, no making new features, none of that. Obviously we have to talk about migration of existing code base. You have to make sure that if you have a C89 code base, you can port it to C11 or even to C23. Not quite fully possible without some tweaks, but I think we did a decent job there. And then C23, obviously, you're self-documenting applications. But more than the principles of the charter, it's used in internet arguments a lot, and in committee arguments a lot. I get to hear the spirit of C so much, to the point that it actually drives me insane. Every time I hear it, I want to take off the headphones. I just want to just God, I don't want to hear this. But I have to hear it. This is the phrase that gets thrown at me so much. This isn't in line with the spirit of C, and I just oh God. It's a very common cudgel, right? But why is it a common cudgel? Why does it keep showing up? Why do people keep telling me that this isn't in line with C, right? When we talk about defer, I keep hearing that, oh, this is garbage and it is in line with C, and you should have to keep the language small and simple, right? When we hear about constant expr, we hear, oh, it's not in line with C, it's erasing the ability for a compiler to do optimizations at compile time or runtime, whatever it wants to. You shouldn't be able to do that. It's not in line with the spirit of C, right? Almost every feature, VLAs, complex, imaginary, a lot of library functions, right? All of them, is this in the spirit of C? Somebody always says no, and it gets confusing, like, who are you supposed to be trusting here, right? Because sometimes they say no to stuff that looks like they should say yes to it, and sometimes they say yes to stuff that you think they would say no to, and it doesn't seem like there's any consistency, and it drives me nuts. But I hear it a lot, the spirit of C. Again, Father Christmas bothering me. It gets applied to everything, literally everything, right? New stuff, old stuff, stuff we put in C23, stuff that was there a long time ago, right? If you use generic, you should be fired, right? That kind of thing, right? Constant non-security, complex shouldn't have been there. Embed didn't need to be put in. Lambdas shouldn't be put in, right? Why do we have atomics when we have volatile, right? Which was a very fun discussion, and by fun I mean depressing. Obviously, atomics were not in the spirit of C the way we standardized them, right? And that whole conversation drove me absolutely up the wall. And the reason some of these have asterisks there is that we actually only started saying this after we adopted the feature, right? And after we saw that it wasn't picked up very quickly in the ecosystem. So we kind of, it's an ex post facto justification. Like, oh, it didn't get good adoption. Must not have been in the spirit of C. We should roll it back. And in some cases, we did, right? Variable length arrays, complex, imaginary, and a couple of other things when were standardized in C99. They were made mandatory features in C99, but when C11 came around, we kind of rolled a lot of them back and made them optional. And again, this was idea because, well, adoption is slow and they're not really seeing that the implementations might not be good, right? Along this time, we were also getting a lot of, vulnerabilities off of the stack. Thanks, VLAs, where people would, not take an unsanitized number and use it as the runtime parameter into an array, and that created a VLA that would either blow up your stack or manage it in a way you didn't expect, and things would go wrong very quickly. And so a lot of people had misgivings about things like variable length arrays and other things, and so kind of retroactively after they were standardized to kind of put us on par with APL and Fortran as like numerical computing languages, we then rolled it back and said, it's optional. You can throw it out, right? And so a lot of compilers do throw it out. MSVC in particular throws it right out the window. So, obviously we want to adhere to this charter, right? We want to adhere to this document that tells us what we're supposed to be doing. Everybody says that we're abandoning the spirit of C or that we're adding complexity, we're you know, we don't have enough user experience or commercial compiler experience. It has to be a commercial compiler, by the way. You can't just like tinker some compiler yourself. They put a clause in it needs to be a commercial compiler. So you got to be getting paid for it, which sucks because I'm not getting paid for a lot of the work I do. Unless I can swing my GitHub sponsors as payment for the compiler. I don't know. I'll figure out how to make it I'll make my implementation a commercial implementation. I'll figure it out. But it has to be a commercial compiler that has the experience with these features. You can't be too inventive, obviously, and you know, you can't be using new features for all the stuff that we've been doing above, right? So how do we adhere to this document? How do we make sure that we're adhering to the standard? How do we make sure that we're pleasing people who, you know, kind of have been for a very long time saying you're ruining C, you're ruining C, you're ruining C, you're ruining C, you're ruining C. So let's talk about some of those features, right? Because like, if we're going to say that VLAs or threads or atomics or generics ruin C, right, we have to find where we failed the charter, right? That would be a good place to start, right? So that we know where we failed, so that we can, you know, stop failing, right? Like it's like a post-mortem sort of deal, right? Although it's not dead, so post-mortem isn't the exact right term, but like we're gonna do a little small dissection, right? Yeah. So variable length arrays and variably modified types, VMTs. This was actually originally proposed by a man by the name of Tom McDonald on behalf of Cray. Cray, C and C++, Cray Research. Some of you might have never heard of them, but if you're in the numerical world, they're all over the place because they are huge in national labs. And they're also huge in, you know, not just national labs in the United States, but labs all over the world. They were the ones who cooked up VLAs, right, as we know them today, right? They made the feature, right, back in, 1994. And I kind of have some checkboxes here about things they kind of adhered to the C99 principles, right, that were there at the time. So, you know, they had 3 years of secret proposals and editing, so there was lots of back and forth, made sure everybody was in error. They didn't really rush the process. They were trusting the programmer, right? I mean, it's VLAs, right? You're typically supposed to allocate something on the stack. So, like, you're responsible. Don't blow out your stack. Don't, you know, connect it to unsanitized user input, right? All that stuff, right? We are trusting the programmer, right? That turned out to be a mistake in some cases, but like we were following the charter. It was implemented in multiple compilers, right? So this wasn't pure invention where somebody just said, I have an idea, and just like scribbled it on the back of the napkin and like folded it up and then like mailed it into ISO. This was actually implemented in places, right? So obviously Cray C and C++ had it, but then this was around the time when there was the, I wouldn't say violent, but there was the explosive split between GCC and eGCC, where they parted ways from one another, right? So they forked GCC at a time. And so for a while, there was like, it wasn't quite Red Hat, but it was basically Red Hat-ish folk who forked GCC and basically maintained their own version and vastly improved it. And they improved it so well that it was around that time, around the 2.x date, I think 2.8, 2.9, 2.95. They merged back into the GCC main tree and they became the actual stewards of GCC, right? So that was where, and around that time, they also had support for VLAs, right? And there were other compilers as well that also had support for VLAs. So we have multiple commercial, widely used implementations, right? So we're following the charter. Now, some things that people want to ding it on is that it's not simple, right? It's runtime, right? So you've taken size of, which is originally a compile time thing, a constant time number, right, that you can use in various different places that require integer constant expressions, and it would work, right? It would give you, you know, statically sized arrays. You could, you know, use it in certain computations, and it would do exactly what you would expect it to. Then we try to change it to this runtime thing, right? So you have the same syntax, everything looks the same, but it has subtly different properties. And the other issue, and this is kind of after the standardization of VLAs, it messed poorly with existing implementations. So a lot of implementations didn't have a lot of stack to give, and a lot of implementations didn't have a heap. So where is this runtime data coming from? And the standard was very quiet about that, right? We don't really say where this memory is supposed to come from, right? It is a conforming implementation that you can pull VLA memory off of the heap every time. You could just call malloc every time and then call free at the end of the block, and like that's valid. That's a valid implementation. I wouldn't recommend it, but like, go for it. So it meshed poorly with existing implementation. A lot of people had trouble implementing it, and they also struggled with suddenly having this runtime size of. And consequentially, down the line, as we got things like a line of and other things that were supposed to like compute the things at compile time, those things became runtime entities when you put VLAs with them, right? And so this became kind of like a very big contention point. Like it felt clunky to use, and not everybody was implementing it correctly. And what was it? It wasn't until 2020 that GCC actually implemented what's called stack probing, which is really just check the size of the stack before you decide to allocate this huge buffer off of the stack, so you don't like blow up the stack, right? So it'll segfault instead of just like going off into space. And so, it took a long time for implementation to get kind of even remotely decent with VLAs. And so that had a very negative impact on a lot of people who were using it, right? So they noticed the code gen was bad. They noticed that a lot of the features were just not up to snuff. And so it kind of contributed to this nasty feedback cycle where everybody was like, they want to use VLAs, but like they have this bad code gen, and it's difficult to control where the memory comes from, and how does your implementation implement the feature, right? I don't have any control over this, so I just have to depend on my implementer. But what if my implementer's not necessarily hostile to me, but they kind of phoned it in, and they did whatever, right? And they didn't add any of the bells and whistles that I needed, right? And so it obviously it was obviously difficult, right? A difficult time for a lot of people. The numerical people were happy, though, because, again, they exist on their own planet, in their own island, with their own supercomputers. They get their own compilers. They can hack them up as much as they want to. So they were partying, right? They were like, yeah, VLAs, we got it. We got VMTs, we got VLAs. They're on cloud nine, right? But this is kind of what VLAs look like. And honestly, it kind of checked all the boxes, right? Except for the runtime size a bit. But even then, this was back in '94, right? Like, compilers were barely doing constant propagation back then, right? Like, do you really need a constant time size of? I mean, it turned out to be super important later as we got like better compilers that could do better optimizations, but like, I mean, did you really need it? And so it turned out, yes, we did need it. It was kind of an important property, but we degraded into this runtime size of and all these interesting questions about when the type of VLA is made available and whatnot to the end user. And so that kind of became a contention point. But like, for the most part, this passes like what the charter asked of it, right? So even though retroactively we say it was a bad feature, right? Like at the time, it checked boxes. It checked the boxes. It had implementations. We knew how to implement it, right? That sort of stuff, right? Threads. Threads.h. Actually proposed back in 2005. Had a lot of experience, which is weird because when you read some of the papers, especially Martin Seaborg's, he's like, oh, there's only like one implementation of it, and like they didn't know what they were doing, and we standardized, unbaked stuff, right? But it turns out it was actually well implemented. It was actually, in fact, a joint effort between WG21 and WG14. It was around this time that like both C and C++, both committees were like swapping papers back and forth. They were really talking to each other a lot, like almost every meeting, every time, right? And so they did this kind of together, right? And it was implemented and deployable on multiple platforms. Now, we didn't get threads.h exactly, right? But we got xthreads.h on MFC Windows because Windows can't help themselves and can't be standard with anything. And we got, obviously, a form of it based on libpthreads. Now, the libpthreads version was a little bit late to the party. When this stuff first got proposed and eventually standardized in C11, the threads.h didn't come for like, another 6 years on GCC? They could have implemented it, but I think there just wasn't any pressure because they weren't really doing much code sharing, and everybody was using libpthreads. Pthreads was basically the way to do threading on anytime you want to touch the Nix machine. So it didn't really manifest very quickly, and so it didn't see much use. And so at the bottom there, you can see not implemented by most vendors. It was because of this idea that GCC took such a long time to implement it. Microsoft still hasn't implemented it, though I've been told down the down low that they're implementing threads.h, and maybe they'll get it in their compiler eventually, which would be great for MSVC, but it's not implemented yet. But it was very much a collaboration between a lot of different people from both the C and C++. There was a lot of implementation experience. There was a lot of eyes on it. So this wasn't quite half-baked. It just, we had all the buy-in. We had all the people there. We standardized it, and then it took such a long time to actually get off the ground, right? And that's a little bit weird, right? It's sort of the same story with VLAs, right? Like we standardized it, we knew what we were supposed to be doing, and then people kind of stumbled a lot in implementing it and getting it on platforms, right? And so it was a bit of a weird thing, right? Like we had this standard thread facility that almost nobody was using because they would rather just hit the platform-specific API to do it, right? Or in some cases, some people would literally wrap C++'s stood thread and use that to create their own platform agnostic API, which is just like, what? Huh? But that's what we got. So that was kind of the trouble with thread foundation. And again, it was mentioned by a couple papers. It was mentioned by a couple people that like this was like a reason, this is like a one thing that we failed to do properly in C11. But again, they kind of did everything right, right? They had the joint effort, they had the multiple deployable implementations, they had all the stuff that would qualify it as a feature for C. But kind of, again, retroactively, we say it was a bad feature, right? And it seemed most of that stemmed from the fact that it just wasn't implemented by our vendors. Atomics, this one's super fun. And by fun, I mean painful. Lots of talk about this one, right? This one spent more time baking than thread stuff. The thread stuff kind of came with the atomics. But the atomics were the really big part, because at this time, this is when everybody was like losing their minds about the memory model in C++, right? They weren't able to like, there's no well-defined way to like talk between threads, data races, how do you share stuff, right? And so in C11 and C++11 and later iterations of C++, they really hammered down on the memory model. Like, what does it mean to have a data race? What is that happens before relationship for our code, right? How do you, define reordering optimizations and so on and so forth, right? So originally, this was implemented as a library at first, right? This was what like Hans and Lawrence and Paul McKinney, who's a prolific Linux kernel contributor. Crowley obviously does a whole bunch of numeric stuff and lots of asynchronous work. And Hans is just, again, a titan of just multi-threaded programming, multi-threaded modeling and everything, right? He powered a lot of the work to get this model for multi-threading into the standard, right? And so you have all these powerhouse people working together. They implement this stuff. They share their implementation. They share their notes. They're sharing between C and C++, making sure that everybody's up to date. But one of the things that they actually discovered, which is what you're supposed to do, right, when you're getting user experience by testing stuff in the field, they tested the fact that they had these libraries, and they would deploy these libraries, and then the compiler would reorder their crap on them, right? And like that's not supposed to happen, right? You're not supposed to have a compiler that reordering your atomics beyond its fences and everything else, right? And the reason it was reordering things beyond its fences is because the compiler didn't understand that like this was like a fence and I'm not supposed to do that, right? So there was always this game of cat and mouse where they would deploy the library and then the compiler would be like, oh, I'm smarter now. And then they would start reordering stuff again and they'd be like, no, stop doing that. And so what eventually ended up happening is that, especially for the C standards committee, right? Because again, they don't have the same kind of commitment to overpowered library features like C++ does, they said, listen, we can't kind of keep playing this cat and mouse game. We have to give the compiler a set of things that it knows about for sure, so that it doesn't do things like reorder fences or anything else, right? So we have to bless certain things, bless certain operations, bless certain types as atomic, as having these properties, so that we can get the ordering guarantees that we wanted in the first place, right? And so that's why this thing that was started as a library had to transition into the compiler, right? But that's invention, right? So people like freaked out, like, whoa, hold on, you're doing invention here. We shouldn't be doing that. But they explained themselves at the time, like, listen, like if you do this as a library, you're going to be forever playing this game of cat and mouse, or you're going to have to request built in from your compiler anyway, so they stop reordering your stuff. Like at some point, the compiler has to be aware of what's going on. You can't just do this as a library forever, right? And so that's why it became something built into the C language, right? Now, unfortunately, that caused a lot of issues, right? A lot of people want the atomics that happen in C to match up kind of pretty perfectly with the ones that happen in C++. And it turns out that a lot of implementations weren't really communicating with this. Like glibc wasn't talking to libstd C++ when they implement their atomics or whatever, right? And so there was cases where you would attempt to use an atomic int from C, and you'd pass it to a stood atomic of int to C++, and it was not ABI compatible. It was not compatible in any way, shape, or form. And so things just broke in horrific ways. And it meant that you couldn't mix C and C++ code. So now we have a compatibility issue, right? So you have C code that you want to write atomics with, and then you have C++ code that has atomics, and you can't mix the two, right? You have to like serialize and bridge, and that's obviously slow because you're trying to use atomics, trying to go fast, trying to reduce contention, but now you have to introduce these manual sync points to make sure that you're doing things the right way, right? To sync between the two languages. And so usually what happened is somebody either completely abandoned C++ atomics and went with the C ones, or completely abandoned the C++ atomics and went with the C++ atomics and went with the C ones, or vice versa. So that was a pain. We also, of course, had a little bit of a usability issue with the way we made them types in C. So you can be a qualifier, you can atomically qualify a type, or you can actually make a type out of it by doing _atomic and then putting the type in the parentheses. And these are supposed to be like identical-ish, but it has interesting. Being a qualifier means it has being a qualifier means it's like const or volatile, right? And that's not great when you're doing certain kinds of programming, right? And it also kind of violates the mental model that some people have about, like, I can drop qualifiers or I can gain qualifiers, right? And so it didn't actually work like that. So this qualifier version sort of made it difficult for some people to program, but other people loved it, right? Particularly numerical people, because they wanted to do something like, say, _atomic int star, and say this is a atomic, this is a pointer to an atomic integer, right? And they want to basically access it like it's an atomic. And so for them, that was really good, and they wanted like lots of ABI. There was a lot of people who wanted a lot of different kinds of ABI styles, right? And so typically what the two different ABI styles you could have would be lock-free atomics, where the CPUs, so the CPU can guarantee that if any operation that you're doing on, say, an integer or a car or a double, or maybe not double, but whatever, could be guaranteed to be done in a certain amount of time, that would always happen, right? It either happen or doesn't happen, right? So either you observe it before it happens or you observe it after it happened, and there's no like racing there. The other approach is obviously not lock-free, right? There's a lock inside, right? So there's a type, you have the actual value stored in there, and then you have a lock next to it, or you have a lock table stored nearby somewhere. And so the whole point is that there were mismatches between C and C++. There were mismatches even internally in implementations about whether they were lock-free or not. And that prevented a lot of people from sharing the stuff. And obviously, if you have a lock-based implementation, it could be a little bit slower than a lock-free one. And so some people wanted to be able to do things like, oh, if I have an int star, just a plain pointer to int star of a bunch of data, I want to be able to make an atomic pointer to that and then access each integer atomically. And like, did that work? Was that supposed to work, right? Depends if it's lock-free or not. And so it was hard to kind of guarantee that stuff. And so that's why atomic was kind of really rough for the usability. Which was strange because we didn't catch this, even though some of the stuff was implemented, we didn't kind of catch that. And you probably wouldn't be able to catch it until much later, right? Because it's not something, whether or not your type is lock-free is very much a platform-dependent choice, and you only really figure that out until you like get down to the platform and you start mixing and matching and doing lots of big code. And so even though they had like between them implementation experience and between their compilers, like they were all self-consistent, right? When you start handing it off to vendors, they can do whatever they want. And again, quality of implementation, right? So they could be lock-free, they could be not lock-free. And so vendors freely mixed and matched for whatever they could get out of their platform, right? And sometimes they made suboptimal choices, but because of the application binary interface, ABI, they couldn't change their implementation. So even their suboptimal, it's like, well, we got to keep it because we got to make sure that we're stable. If you take some, C11 code and it compiles it with C23, even if we know better in the C23 code, like we can't change it to a lock-free implementation because our ABI is just like that, right? And so you have all these issues surrounding atomics that, despite kind of passing the initial muster and kind of being a ready feature as far as C11 was concerned, still ended up failing kind of in the final leg because of these compatibility issues, right? And again, it's hard to see that coming when you're with your people who know what they're doing, and then you kind of fan out and you go to exotic platforms and you go to different places that you don't have full control over, and now things don't quite pan out the way you expect it to, right? And so that was kind of a large motivation for what's going on there. Oh, I went too far. Generic, also called out as a terrible feature that you should get fired for. But this was actually originally conceived by PJ Plogger, who also worked on one of the most, I guess, well-known STLs, the Dinkumware STL, which got used in a lot of different places and was actually bought by Microsoft, and it actually was the foundation of their STL that is currently in the GitHub repository. It was sourced from existing practice, but it wasn't exactly the same as that existing practice, right? So GC had this thing called built-in choose expression, where you would give an expression, then you start listing out some types, and it'd kind of be like an if tree, where you say, if it's this type, then do this. Otherwise, if it's this type, do that. Otherwise, if it's this type, do that, right? Generic, the way it works is it's kind of more like a switch statement. You say, here's all the types, and you only match one of them, right? So it's a little bit different than built-in choose expression. It was picked up and implemented, and the reason it was picked up and implemented by EDG, and I think possibly Intel at the time, was because they were having trouble implementing what's called type generic macros, which we'll talk about in a second. But they basically proved it could work and it could solve the problem without introducing C templates or function overloading. At the time, there were a lot of math functions that they were adding to C. If you ever looked at the like Annex F or Annex H, you'll see like a million different like floating point functions. In fact, for C23, we added like, what was it, over 500 new math, like floating point math functions. But there's a lot of those functions, and so a lot of people want easier ways to program that stuff. And so they came up with this idea of type generic macros. And kind of on the behind for some of this, what they were doing is they were abusing function overloading, right? Which is a feature that comes from C++ and is not really in C. But they kind of said, well, we're just going to standardize these macros, and you'll put the arguments in there, and then, you know, through some magic, we'll know whether to call a float version, the double version, or the long version, or the long double version, or whatever. And so that's kind of what happened there. So it was implemented. It did have existing practice. There was a slight bit of invention, obviously, going from built-in choose expression, which was more like an if cascade, to generic. But they proved it could work, and they was able to do it without introducing templates into C or function overloading, right? Which was kind of the main driver, right? They didn't want to. The committee explicitly rejected overloading, or that kind of overloading as a solution for C, right? So they had to do something else, right? This was like, then again, to kind of talk about this, right? This was the TG math header, right? The type generic math header. This was part of a technical specification, right? So again, they use this technical specification mechanism, a TS, right? They can ship things out in the world through this document early before the standard goes and get experience with it. So they got all this experience with it. They understood what the TG math is. But the overloading features were rejected before, but the TG math was still kind of going through the committee, right? And they wanted it. So they said, okay, we need generic, right? And so this is kind of where generic was born in the first place, right? There's actually some very interesting papers where people are like, hey, so I'm trying to implement this generic function thing, and I can't because there's no mechanism to do it in C. And normally that's okay, because one of the things we say in the committee is that it's okay if your library performs magic, right? Your implementer is allowed to perform magic, right? So for example, in offset of, you can take a null pointer and create a pointer to something, and then go to the member inside that null pointer, and then subtract that from null pointer to get the offset to the member inside the thing, right? And that's like a favorite language lawyer question, right? You go to Stack Overflow, you ask about offset of, it's like, can I implement offset of in standard C? And then you get like a million answers like, no, you can't. Yes, you can. No, close. We already answered this before, right? You know, all that stuff. But like, your library is allowed to do magic, right? But this was too much magic, and it was more than most implementations can handle. And so that's why they needed generic, right? They needed a way of saying, listen, if you give me a float, I will call the float version of cosine, right? If you give me a double, I'm going to call the double version, and so on and so forth, right? And then, you know, you get, you know, these quadratic versions where, you know, you're passing two arguments and you have to pick the right one, and it's very fun. But that's where generic came from. That's where TG math came from, right? And again, these were things that were implemented and shipped, and so nobody's really violating the charter with any of this, right? They're kind of having to do a little bit of invention, which is a violation of the charter, but like, it's in service of these features, right? And you're supposed to allow to balance the idea, and they did implement generic before they actually standardized it, so like, they kind of checked all the boxes, right? And so what we're really seeing is that maybe these features were not all that ill-conceived, right? Like, sure, it's not like, don't get me wrong, like, VLAs are not my favorite feature, and neither is generic, and a bunch of other stuff that's in the C, but like, these things didn't violate the charter, right? Like, they weren't doing the wrong thing. They weren't making the wrong choices when they were doing this, right? They were following all the rules, insofar as they could follow all the rules for being put in impossible situations, like the committee is considering some kind of overloading and then kind of swaps it out from under you while you're trying to standardize your well-considered stuff. So, you know, maybe it wasn't the features that were ill-conceived, right? Again, not that there aren't room for some improvements in this stuff. You know, for example, VLAs and VMTs have a lot of holes, right? So this syntax looks super ugly. Don't worry about it. But basically what I'm doing here is I'm passing two sizes, and then I'm using those sizes to create a pointer to VLA, right? And the reason I'm creating a pointer to VLA is because I want this pointer to VLA, this variably modified type, to hold its size, right? And the idea is that if I use size of star p, right, it's a runtime thing because again, it's a variably modified type. I can get the size out of this, right, without consulting m or n, right, directly. And so this seems like, hold on, does this mean that we have bounds checked arrays, like arrays where we can do bound checking or pointers where we can do bound checking in C, right? Like that would be pretty cool, right? Except not quite. I have n equals 2 and m equals 3, right? I put them in a VLA and I create a pointer to VLA, right? I malloc my VLA, right? And this is how I get a variably modified type. I just get a pointer to a VLA, right? And so you can malloc these, right? This is, again, probably blowing certain people's mind. Numerical people are all up on this stuff, but this is the stuff they don't tell you about, that they're using all the time. But you can malloc this, right? So now I have a pointer to an array that contains its own size, right? So if I printf the size, right, that's that first printf is 24. If I print array size and I pass in n and m unmodified, I get 24, right? So like it's contained the size properly. I then modify m to be 4. I then printf the size from locally, right? Just directly referencing p. And I get 24. I then ask to print the array size, and now the size is 32. And this is where VMTs fall on their face. This is where VLAs fall on their face. You can lie about them, which is fair because you can lie about any pointer in C. But like this, I thought this was going to be like the Holy Grail. Like, oh, finally, I have a sized pointer. I can do something with this. I can make something happen with this. I can put some safety in some code bases or something, right? And I can, but only if people don't lie. But like the entire point of things like Heartbleed was that it lied about the size. It was a mistake. They didn't mean to, but it lied about the size of the pointer. And then they just read a bunch of stuff they weren't supposed to, like everybody's secrets, and then dumped them out to attackers. And then they had access to everything. So VLAs didn't learn the lesson, right? We still get to lie, right? And so we're like this close to like we could have a syntax where like, because you can see this, right? Even though I modify m and n in this function, I print for the print locally for p, it's still 24. So like the size is stored in the VLA. The VLA knows its size. So, but when I pass to a function, it's just like, well, I'm going to throw that size out the window, and then I get 32 or 800, and now I'm reading data I'm not supposed to, right? Now I'm accessing things I'm not supposed to. And that's emblematic of C, right? You know, you pass an array somewhere, it decays to a pointer. Where'd the size go? Who knows? And so this was this close to being like the solution for stuff, and then it stopped being the solution for stuff. But again, this is what I say when there's room for improvement for some of these features, right? There's room to make them better, and we haven't quite utilized ourselves to do that yet. Similarly, generic loses qualifiers and array information, right? So if I have a constant n and I want a generic on it, and I say, oh, I know this is a constant n, I'm going to match on the fact that it's constant n. That doesn't work. If you're on Clang or GCC, like a recent version, it'll warn you and say this branch, this constant branch will never be reached. Because when you do generic, it strips off qualifiers and it strips off array information. So arrays will decay into like pointers or... Yes, I think so. Someone double check me on that. They decay in the pointers, right? Probably. Yeah, I mean, it's... I think you might be able to match specifically on the exact size of an array, but I think it might also just it might just decay. But oh yeah, there is a pointer conversion. Okay, yeah, because right, so it performs L value conversion, which is the same thing that happens on when you pass things to a function call. Yes, sorry, that was nerd speak for it decays. But you can't do this, right? You can't match on the fact that it's constant n. It strips out those qualifiers. So like you can't match on that stuff, right? So if I wanted to implement, say, is const or is array or is some other kind of way of implementing this, I just can't do that. You know, I will just get return one. I'll just get one here. The expression will return one, and then we'll just kind of go on our lives. So we lose the ability to do some kind of very cool matching and stuff that normally we would be able to do in maybe other languages, or if generic was a little bit better than it is. Fun fact, Aaron Bauman isn't here, but Aaron Bauman actually implemented a version of generic where if you wrap this N in type of, which I standardized for C23, so it's now actually you can use it everywhere, assuming MSVC catches up. You can wrap that in type of, and then they have an extension where because you're passing a type into generic, it will actually keep the qualifiers and keep the array and not do L value decay. So fun little, for all of you who are here, you get this little fun little Clang secret. And that's when you can start doing like is const and do it like normally and cool and stuff like that. But that's like advanced like C meta programming, and like that's something I'd give a talk on or something later. Thread-slot obviously we're talking about its weakness. It's not everywhere. It's not on Microsoft Visual C, and a few POS-based platforms don't have it because they just say, well, I have pthreads. I don't need this threads.h nonsense. And then you write code and then it just fails because they don't have it, even if it's perfectly capable of being on that platform. And so that kind of suffers in that way. There's also other existential problems, right? Enumerations cannot be size controlled, right? Undefined behavior obviously continues to punch people in the face. We're actually not standardizing a lot of existing extensions in practice. So like statement expressions, really cool stuff. Nested functions and blocks, really cool stuff that we haven't standardized, right? There's also ABI problems, right? So the 32-bit time, and specifically the 2038 problem, right? It's not necessarily like, oh, we need to use 64-bit time. That's if we change the 64-bit time, we break every program that was depending on time t being a 32-bit value, right? And so we need to be able to do things like fix the application binary interface, be able to patch those binary interfaces without blowing up the old code. And we don't really have any tools to do that, which hilariously, other platforms have already figured out how to do this since like 25 years ago. BSD has a way of solving ABI, and they solve this problem. It's literally an example on their wiki on like, yeah, this is how we solved this problem like 25 years ago, and I wish people would solve it in the standard. And we haven't done that yet. So again, more existential crisis in the standard. And so, it's 2023, right? So where's our portable bit function, right? Where's our SIMD? Where like C is built as this access to the hardware language, right? Even though it's supposed to just be a normal high-level abstract machine, right? It's built as access to the hardware, the fast language, the dangerous language. You can do all the cool stuff. Okay, but I can't even use my XMM registers, right? Like, I can't even do portable bit packing on my structures, right? Without getting a drank, getting a manual, and then praying a tribute pact or pragma pact 1 or whatever gets the job done with all the crazy bit stuff. Which you would think that this is such an old problem that it would be solved by now. But there's compilers that pack things differently than like GCC or MSVC or whatever else, right? So not piling on this implementer, he implemented it the way he did for a good reason. But SECC does things differently than GCC, and that has actually resulted in a lot of people like, hey, I'm compiling for libu. I'm trying to compile something for libu USB, and I have this structure, and I'm trying to put it on the wire so it goes to my USB device, and it actually is not correct. And it's like, well, it's because we do different packing for our structure, even if you use a tribute pact, even if you use these bit fields, that is different from GCC. And that person is effectively up, Bleep Creek without a paddle, because, it's just implementation to find what happens with your structure, right? Where do the bits go? Who controls those bits? Right? Like, it's just whatever the implementation decides to do or feels like doing that day, right? And we haven't solved that problem, right? Which is really weird because the Ada programming language solved this problem like in the 80s. And like we keep writing papers like, how are we going to solve this very difficult, tough problem? And it's like, just look at the language right there. But we don't do that. Unicode conversion functions, obviously, I'm a text guy. That's how I actually ended up getting down to C in the first place. I was asking too many questions about locale and text, and I ended up down here, and now I'm the product editor. So Unicode, not even once. But Unicode conversion functions are something we don't have, and that's kind of my fault. It was supposed to be in C23, but I didn't get it in time. And then, of course, we have a whole gaggle of POSIX style functions that kind of affect global mutable state. We want to be able to call isUpper and have it kind of be consistent. You usually think it'd be ASCII or something, right? But, it changes based on the locale. And so you get different kinds of behaviors and performance characteristics from isUpper and things like that, right? Because it's tied to the locale. And so that's all kind of controlled by global shared mutable data, right? That implies locks, that implies bottlenecks in your algorithms and whatever else. And so now you're kind of suffering. And so again, it's 2023, and like, where is the stuff that would make this all easier, right? Why haven't this stuff been solved already? Why haven't we gotten to a place where this all is kind of cleaned up and makes sense? And if we're relying on standardizing existing practice, right? And existing practice in many of these cases, like for the ABI from FreeBSD and other places, has fixed this stuff. Like, why haven't we actually gone and done it? And that kind of calls into question the charter, right? Like, so I had to get my hands dirty, right? So for C23, right, this is the first standard release I've been a part of, right? So I started doing things to get involved, right? And that's how I got, like, again, like I said, I did Unicode, not even once, but I did it, and now I'm neck deep in this stuff. So we got bit functions, right? Now we have bit functions that describe like things like endianness and 0 leading ones and all this other stuff in the standard now, and they're all part of the standard, right? They're going to be shipping with C23. You should be able to access them. They should give you direct access to all these intrinsics and everything else that have been on compilers for, I mean, come on, some of these instructions are literally like from the 80s, literally Intel 8080. Like, why did it take so long to get here? But anyway, it's there now. It's there now. I made sure it's in there now. So we're all good. We have endian stuff and we have bit operations. We have to get the rest of the bit stuff in later, right? Enumerations, I fixed those. You can actually add a colon after the name of the enumeration and then specify a type, right? This is similar to C. If you're C++, this is like, wow, this is old news. But like if you're C, this is like, oh my God, finally, right? Because now you have dependable data types underlying your enumeration. So you can put them in structures, you can generic match on them, and they have the expected behavior, right? All of that stuff. So that just works the way you expect it now. We also have checked integer stuff, right? Mentioned earlier in the panel and in Robert's talk and in other places. But now we have standard way to opt out of undefined behavior for integers, right? So if you want to do a wrapping add and you know that's what you want to do, then you use the checked add function or the check sub function, right, to do subtraction, or check mul to do mul. We didn't include division because there's only one case where division is UB, and that's if you're, I believe it's if you're dividing, it's not the 0 by 0 case. It's like if you're dividing int min by something. By -1, yeah. And that's the, I mean, we should probably add ckd div anyway, just to cover that case, but it's simple enough. I mean, we say trust the programmer, but like, this is also a security feature, so maybe we should just add check div, right? But, we didn't do that. And also implementations didn't have check div. Like GCC has built-ins that map to the ckd add and ckd sub stuff, and like, they didn't have a div, so we just didn't include it, right? There's a hand back there? Yes. Microphone.
So you don't do check div. I'm assuming you also then don't do check modulo?
We don't have
this has the exact same overflow.
Yeah, we don't do check modulo.
Okay.
Yeah.
Yeah.
We only have these three. We only have checked add, checked sub, and checked mul. So again, we probably should add those, but it's a topic for another time. But you can do this, right? You can do ckd add, right? So I'm initializing this uint32t to 0. We added empty brace initialization. That was an extension that was implemented everywhere. So I was like, it's very silly that we don't put this in the standard. So I did put it in the standard. So now you can just use empty braces, and that means you can initialize everything with it, and it will 0 the bits, including the padding bits, which is different from C++. In C++, the padding bits will be whatever. With C, when you do this with the empty brace, you'll get padding bits that equals 0, right? Which means it's also secure to use in your kernel. Right? Just fun fact. So that will work, and you can use the Boolean to check if it did wrap, and obviously you'll get a Boolean back that says it did wrap, and then the value is 0, right? Because you did 1 plus uint max, and so it just rolls over 1, and so you get 0, right? And so well-defined behavior, no UBSAN won't trigger, all that stuff is good, right? We also have proper keywords now, right? So we got our hands dirty and we said, all right, we're sick of this whole underscore bool, underscore capital S stuff we're doing with these keywords. Like, let's just make them real keywords. And so we did. So you don't have to include a header anymore. You just get these keywords, and you get false and true and all this other stuff, right? There's some mitigation techniques we had to do for false and true to make sure that we didn't break anybody, right? And so vendors can do, hash define for their true and false to make sure that, your people who are checking for if true or if false will not be broken and stuff like that. But we did add some mitigation for that to make sure that they're okay. And a ton more. Like, this is actually 2 pages of what's called Annex M in the standard that just lists a bunch of changes we made. A lot of the changes we made, right? And we have to ask ourselves, like, maybe the common denominator was never existing practice, right? We kept going harder and harder in, like, no invention without, no inventing stuff, no exceptions, right? Always standardized existing practice. right? But the things we added solve material problems that actually will help people. And in this case, for a lot of these cases, this is stuff that like implementers did do some of these things, but for most of the changes that got in C, they came from people, right? Tom McDonald put VLAs in the standard because he had a numerical computing background. He wanted C to compete with Fortran and APL and the other languages that he was using in his lab, right? Hans Boehm, right? For the atomics and the memory model, right? He did tons of work, right? He's still active in the committee. He's still doing work for atomics and the memory model, right? In both C and C++. You know, people who fight against status quo, like Jens Gusted, he's the one who's responsible for the keywords. He's fixed up several language and library features, fixed up atomics, a bunch of other stuff. Aaron Bauman, who's not here, but did attributes, did bitint, right? Which is a variably sized integer, right? Not variably sized as in runtime, but like you can stick a constant expression in the bitint, and you can basically say it's 63 bits wide, or you can say it's 72 bits wide, or you can say it's 24 bits wide, and you can actually choose how big it is, right? So this stuff kind of applies directly to FPGAs, where you want to be able to precisely code how many bits you're using, right? Save, you know, on your FPGA's resources, right? And then of course we got things like constexpr and VA start with a list without having to pass the first parameter. So you can have a ... function in C that doesn't require a first parameter anymore, right? So you can literally just have a plain ... and then just go through the list as normal, right? Without any kind of like extra format parameter or like number parameter or whatever telling you what to do. And all of these came from people, right? They didn't come from implementations. We didn't try to like standardize this in practice. It was just somebody saw a need and fulfilled that need, right? And that was the actual spirit of C, right? This is Dennis Ritchie. I mean, most of you probably know who this is, right? When they were starting to standardize C89, before they started writing charters, before they started getting, you know, they started trying to codify everything, right? Dennis Ritchie changed something about C just before it was standardized, right? In particular, in 1989, right, he made sure that Bjarne's changes in C++, because at this time, Bjarne was actually actively working on C++ and it was a real thing, he actually cribbed the function prototypes. He actually, I would say crib or stole because it was with consent, obviously, but like he took the syntax for actual types with your arguments, because you didn't have that in C before C89. You didn't have types you could associate with arguments. And so he actually took that from C++ and put it in C. And not only did he put it in C, but he immediately deprecated the feature that has his name on it. K&R declarations are named after Kernighan and Ritchie. But this guy knew that what he was going to be standardized, what he was going to be working with, was more important than the thing that had its own name on it. Right, so this is an interview from 2000, but he also writes this down in his writings, right, about the fact that when they were standardizing C89, they cribbed this feature, right? And so we need to be able to embrace making changes, and we need to be able to embrace them the same way that Dennis did, right? If Ritchie can see that something is better and put it in his language and deprecate his own beloved feature, if he can do that, if he can look at that situation and make that kind of technical call, then maybe it's not about how much we standardize this in practice. Maybe it's not about how much we're focusing on, oh, does this come with a commercial implementation of compiler? Maybe it's just if it's a good idea or not. And maybe we should start focusing our charter not on how many compilers implement the thing, but whether or not it's a good idea and whether or not it passes design muster. And if we do, I think that we will see better, hopefully sometime within our life. Thanks.